Hi, HP made a lot of voltmeters, AC voltmeters from the 60s to the 80s, and starting with the HP 400E and the EL and FL, and this is the GL, which is the L referring to the linear dB scale for the AC voltmeter. This is probably the most recent of those models and has a very good range all the way from minus 80 dB to plus 60 dB or minus or 0.1 millivolt to 1000 volts. Anyway, I'll also do some comparison with the HP 3400A, which is the true RMS voltmeter. This one is not a true RMS, it's average responding, which means it can only respond to pure sinusoidal signals accurately. I'll talk about a little bit about the meter circuitry and the basic block diagram that this particular meter has, and I'll do some fairly detailed measurements at different amplitude levels and frequencies. One of the things I had to do to make it work was to not to make it work, but actually to have a cord for this was to replace the existing HP PH163 oval specialized socket with a regular, more modern IEC socket, and that was I'll describe that a little bit. And then one more thing I discovered along the way was while doing some measurement, was I found some DC voltages, rather high DC voltages on the output at the back of the unit, which is used to drive the AC output to as an amplifier. So when I did get this unit, I got it fairly cheap on eBay. It wasn't working, even though the sellers told me it was working, but he hadn't tested it, so he wasn't sure. So when I got it, was totally the meter was fluctuating wildly and wasn't responding to any inputs. So I did have to fix that, which I didn't describe in any particular detail because it was actually very simple. The problem was really the the selector knob was very noisy and it was not making good contact with the various leaves inside the contacts within the selector itself. And being a very sensitive instrument with fairly low impedance dividers in a resistive divider, it was basically not responding to any inputs, and it was just totally wild. So once I got that done, I think the meter was totally functional, and most of this uh, video is mostly about the performance and the other aspects I just mentioned, which I'm going to get into. One last thing, this video is long. It is almost 55 minutes if I timed this correctly. Unfortunately, it just went over what I was initially planning on and discovered a few things along the way, so I just kept going on it. So uh, you might speed up through certain parts of it if you like. So anyway, hopefully you find this enjoyable. Today I'm going to talk about this Hewlett-Packard 400GL AC voltmeter. I have another one which is very similar to this one, which is the HP 3400A, which is quite well known in the industry. At least the last 20-30 years people have been using that until the newer models have shown up. But they are very similar in the way they look, and but there's a key difference among this particular one, the 400GL and the 3400A. So the main difference is that this one is also an RMS meter. As you can see here, it's RMS, but it's average responding. So it's pretty much only good for sinusoidal signals. Anything else like a square wave or a ramp or even noise, it's going to give an error in terms of the accuracy. So it's not going to respond correctly to non-sinusoidal inputs. So before I get into any more detail about this particular meter, I'm just going to describe a little bit about the features, and then at the same time, if I can compare with the 3400A in terms of the specifications and the way they built it. So they look identical, they are the same form factor. This has the banana jacks instead of the BNC, which is a bit of a disadvantage, I think, in terms of not having coaxial termination into this particular instrument, which with the banana jacks I believe there's a lot more likelihood of pickup of external noise. So you have to be very careful when you operate in the very low voltage ranges here, like 0.1 millivolt and 1 millivolt full scale. It has the full range goes from 0.1 millivolt all the way up to 1000 volts, and this is a key difference with the 3400A, which goes from 1 millivolt to 300 volts RMS. So it's got it's basically a decade range selection. The other one has like 0.1 and 0.3 and 1 and so on. So it's got a slightly different scale, but this has a wider scale range. So I think they decided to keep it with the 10x steps here. The other thing it's got is a filter which you can engage by turning the knob to the left over here. And that's a 100 kilohertz filter. I've taken off the cover, so it's actually fallen off. The side cover are similar from the 3400A. The two of them on each side. Once I open up the instrument, you'll see a little bit more into the instrument. And then the other thing that is key in this one is it's got the output is actually an AC voltage at the back, which you can feed in you can use as an amplifier essentially, unlike the other instruments which give a DC voltage that is proportional to the scale that's output on the scale shown over here. And so if you use it in an amplifier, you can get all the different gain settings right directly from this selector knob over here. Of course, the scale also is quite different. As you can see, this one is linear responding in terms of the dB scale, but it's got a nonlinear scale on the actual voltage output. So this does not require zero setting, because there's no such thing as zero, because when you're talking dB scale, it's actually minus infinity when you have a zero volt signal. So it just goes all the way to the left and sits there when there's no signal. And the full scale is really the zero, which is 0 dB, which is the only point where it's you can calibrate it accurately. And of course, they have calibrated it at different frequency ranges to make sure it's accurate over the full frequency range, which goes from 20 hertz all the way up to 4 megahertz. So there are multiple resistors which you can tweak in there to essentially calibrate it at 400 hertz and I think it's 40 hertz or something similar, and then a high frequency one at 400 kilohertz and so on. So it is a very different instrument the way it works. The 3400A on the other hand is got a thermocouple kind of a setup where it actually measures the heat energy that is produced by the instrument after magnification of the input voltage to create a very stable response to a given signal. So even if it's noisy, because of the fact that it's actually using the heat output, it's a little bit slow in terms of response, but it's very stable, unlike a lot of the instruments that if you try to use a oscilloscope or some other meter which does not have this thermocouple type of arrangement, it actually will be finicky and noisy to get a very stable output. Anyway, I'll show that when I compare the two. But main thing about this one is that it's not going to work with noisy signals or with square wave signals or pulses and so on. So it's purely sinusoidal, but for that sinusoidal, it's actually very accurate and more sensitive than the other one, the 3400A. So this is the rear of the instrument, and there's one key difference with the 3400A, and that is it's got a DC input that you can apply instead of AC directly. And so this is all the way from plus minus. There are two inputs, a positive and a negative with respect to ground, and that is minus 35 to minus 55, and on the positive side is plus 35 to plus 55. So you can also operate as a DC power source. And the only weird thing about this is similar to my 3400A, it's got this PH163 plug, which is a unique plug with HP and a few other manufacturers used to use, and it's very difficult to get the cord for this one. This is the cord I've been actually used from my 3400A, which has the same plug. So I'm going to have to most likely remove this socket and put in an IEC socket, which will, because I got plenty of those cards. And I'm not able to buy any more of these. I think they're pretty expensive even if you find one. So there are some limitations about the frequency range and the accuracies and so on that they have described over here. So I think this is a very good instrument to have if you want to measure sinusoidal inputs, and I will demo that in a little while. So that's basically the back of the instrument. And now I forgot to mention, this is the output, AC output, which is scaled up to 1 volt. Whatever input you put in there, you can magnify all the way, gain it up to 1 volt. And so you have to set the appropriate gains range depending on the input level, of course. Here you can see the main board, the A2 board as it's called, which has all the main amplifier, the meter amplifier, the preamp, and the power supply, which is to the rear of the instrument. All these caps are in good shape because I measured all the voltages on them and they seem clean. I looked at the AC ripple and they seem pretty okay, although at some point it might make sense to replace some of these caps, the electrolytic caps. The big round things you see here are the tuning resistors for the different frequency ranges. There's some calibration you can do with that, and pretty much it's all solid state. Most of these transistors are ones that are used, NPN and PNP transistors used in the gain stages. A couple of power transistors over there on the power supply. Other than that, there's not much here. It's the schematic is very nicely done. If you have the manual, one of the best manuals I have seen in terms of the documentation, all the inside voltages and how to debug it and so on. So I was pretty fortunate to be able to use that to find the issue here. So next let's look at the bottom side. The bottom is pretty sparse. There's the power supply transformer right here, which goes into the front of the instrument, or the top of the instrument, to and is rectified and produces the plus minus 45 volt, I believe, roughly DC voltages that is used if you use the AC supply. And this is the main switching attenuator for the range setting, and these are all precision resistors. I think most of them are 0.1%. And the box over here is I believe the input attenuator. So depending on the input level, it's shielded, and it basically will attenuate the signal before it enters. From here, the two wires you see here that go into the main board, and this one is really the post attenuator, which sets the range, whose output then goes into the metering circuit. I can talk a little bit about the metering circuit, as that's probably the most critical part of this instrument, which generates the output voltage which is showing up on the meter, as well as to produce the gain that is sent out on the back of the instrument on the two terminals there. You can barely see the meter over there. It's a regular current meter, I believe, and it's basically configured as in a bridge structure, bridge configuration. So I'll describe that next. So here's the general block diagram of this HP 400GL AC voltmeter, with some specific details shown on the metering circuit. So the input comes in through VIN over here in the main front panel. It's attenuated if required, and goes into a preamp to gain up the signal for small low-level signals. And then there's a post attenuator, which is the main setting for the range settings, which are shown in the front of the instrument. And there's also a filter and so on as part of this network here. So there's an amplifier which uses 2 or 3 transistors to create a fairly high gain, I believe, in this. And just basically we shall represent that as an A. If you go into the manual, you will see that this whole particular circuit is actually described in good detail. So I just wanted to quickly go over the bridging circuit, the bridge circuit over here. So we have the output of this amplifier, which of course will try to maintain these two voltages the same, and this is only for the AC part of it. So there's a DC feedback loop as well, which is not shown in this, and that will set various bias voltages and so on. And there's additional components in here which are not shown as part of the DC network. So as far as the overall AC feedback is concerned, so this output voltage is then driven as a current into this particular network over here, which has this diode and capacitor based bridge network. The difference current then flows through this meter, which is what you see on the front panel. So there are two parts, of course, for the positive and the negative half cycle of the AC voltage. Since this is a completely operating as an AC domain, not DC. So you have the half cycle for the positive current and the negative half cycle. So in the positive half cycle, the meter, they can see the red arrow shows the direction of the current flow through this diode and then down to the meter and back out this way. For the negative half cycle, you have the current coming in this way and then going up and then returning via this path over here down into this current sink. So these transistors basically provide the right impedance level. So looking into this particular node upwards, you'll see the high impedance. Looking down into this, you'll see the high impedance. And similarly over here, you want to make sure this can sink that current, and there's some biasing over here based on this minus 26 volt supply. So essentially this bridge network really sets the accuracy of this meter, and the actual DC levels here are something like minus 9 volts, as if you look in the manual. I measured all these voltages and they look to be well within specs, and I think given that this instrument is probably over 40 or 50 years old, I think it's still performing very, very well. Just shows the level of design excellence that this team that designed this particular instrument had at that time. So here's my function generator, actually a HP 3325A, which will be providing the sine wave as well as some other waveforms that we can try out. Right now at 400 Hertz, and amplitude I'm going to put in as 1 volt RMS. Now let's unplug this. 1 volt RMS, which is right here, and I'm going to connect both of my HP meters are here now. So both my meters, the 3400A and the H400GL to the left, are there. I can only power up one at a time, so I'm going to first initially connect the 400GL, which is got termination of 50 ohms, and then it passes through into the banana jack. Let's turn it on. There will be some initial deflection by the meter as it powers up and settles. So I'm going to connect the HP's generator on this side over here, and so it's a 1 volt RMS, and you can see that it's reading exactly 1 volt on the scale here. Even with a little bit of parallax, it looks pretty good actually. And this is of course an easy measurement in terms of the amplitude level. It's a strong signal. So what I'm going to do next is to cut it down by 10x to 100 millivolts. So it basically goes down to minus 20 dB, which makes sense. So it's 10x reduction, amplitude is minus 20 dB, so it's right at that point. And if I now go to the lower scale, it should go to full scale, and that's what it does exactly now, reading a 1 on the RMS volt scale and 0 dB on the dB scale. Let's go down to 10 millivolts. So this is 10 millivolts RMS, so it's back to minus 20 dB or 0.1 on the voltage scale. And when I go to the 10 millivolts full range scale, it's now again reading 10 millivolts and 0 dB. So it keeps doing that as you keep going lower and lower. I'm going to 1 millivolt here RMS. And back it goes down to minus 20 dB. And this is the 1 millivolt scale, and it's again reading full scale 0 dB. This is where it gets, for my meter, the function generator cannot go below half a millivolt RMS, so I'm going to put that in here, 0.5 millivolt RMS. That's as low as it goes, and you can see that the meter is deflected at the 0.5 here, and which is minus 6 dB, which is half on the voltage dB scale. So all that makes sense. So this is 400 Hertz. Now if I change the frequency, let's make it 10 kilohertz. It didn't move. As you can see, it's still reading half a millivolt. That's the beauty of this instrument. Extremely stable, very accurate if it's calibrated, and it's very nice to use. You can see trends, and that's something you can't get from a digital meter. Let's go to 100 kilohertz, and it's still reading half a millivolt RMS. Now this is where that filter will start coming into play. If I turn it on, you can see it loses 3 dB at 100 kilohertz. And so that's the filter effect that starts to play at 100 kilohertz and above. Now if I go to 1 megahertz, it's reading half a millivolt, and now when I turn the filter on, it should kill it quite a bit. As you can see, it goes off this on the negative side, so it's not much signal left at this point. So that's that for the filter effect. Another interesting thing that you will notice is that, as I probably mentioned earlier in this video, is that the banana jacks have a tendency to pick up noise, even though it's connected with a coaxial cable here. You can see that here. There is still some exposed metal, and there's some coupling coming in some different places. So you'll see that if I turn this frequency down to 60 Hertz, it will now pick up possibly some noise from the environment. So actually right now it's on this scale I'm not seeing anything actually, so it's still large enough that it's not doing anything. We'll try putting a slight frequency offset, 59 Hertz. And then now you can see definitely there's a 1 Hertz oscillation, which indicates there is some coupling coming from the environment. I put my hand in, touch this thing, it probably will change the behavior a little bit as I couple in some noise. It's a power line noise, that is. And then 61 Hertz should give me the same effect. So that's 61 Hertz. So it's beating at 1 Hertz rate. If I go to 65 Hertz, it's much faster, 5 times a second, so it's barely moving, but it's still jiggling around. Anything 10 Hertz and above, it's hard to see it. So if I go to 75 Hertz, it becomes steady again. So that is something that, especially on the lowest scale, the 0.1 millivolt scale, which I haven't shown yet, this becomes critical, that you shield everything. And this is one of the disadvantages if you're operating near the power line frequencies, or any strong fields that may exist at certain frequencies. It'll get into that input, even though you have connected a coaxial cable here, which is even terminated. What I have now is a 20 dB attenuator, 2 dB attenuator in series, terminated into 50 ohms. And this time I can put in 10 times, it will basically attenuate the signal coming from my function generator by 10x. So I should be able to go down to the 0.1 millivolt scale and show you what's going on with that. Right now it's a 100 millivolt signal, and on a 10 millivolt scale I'm getting full scale, so it's exactly cutting down by 10x. So now I'm going to go to a 10 millivolt signal, and we are back to what's going on here. 10 millivolt RMS, I'm sorry, that was peak to peak. So 10 millivolt RMS gives me a full scale again, and now going to the 0.1 scale, I'm going to put a 1 millivolt RMS, and you can see that it's got some error. It's possibly due to this frequency being close to 60 Hertz. I'm going to try something away from that. It's a little bit above that, so there is some extra noise getting in at these very, very low amplitudes. So it's not quite 1 millivolt, a little bit larger. So I'm going to reduce the amplitude down to 0.8 millivolts to see if it comes off the full scale. It's still pretty much fully set there. At half a millivolt RMS, there's still quite a bit of excess noise. So I can't trust these measurements at this setting with the setup I have. It's just not good enough. I think down to the 1 millivolt scale I can use the banana jacks and normal cabling, but anything below that is going to pick up other kinds of interference and just add into the input and cause accuracy problems. I'm going to try this meter next, the 3400, to see if it's, of course, doesn't go down to 0.1 millivolt. This only goes down to 1 millivolt, so I may not see that effect. But this is also an RMS meter, so it may have a different response. So let's take a look at that. So this is the 400A, the true RMS, which is of course responsive to any kind of waveform which is not sinusoidal, and still will give you accurate results. And the technology is basically using thermocouple type measurement, where the heating effect causes the meter deflection. So it doesn't care whether the waveform has got a pulse or whether it's square wave or whatever, sine wave. As long as the crest factor, which is the ratio between the peak and the RMS value, is within 10, it's going to respond correctly and give you accurate values. So at the moment it's reading on a 10 millivolt scale. It's slightly off. Perhaps it's the meter, perhaps it's the other meter was giving me on the dot kind of measurements on the sine waveform. This is also sine here, a waveform, but it's slightly low. I think it's probably the meter off a little bit, but I don't know. Let's do a 3 millivolt RMS signal. So it's going to read full scale on this scale supposedly, and again it's slightly off, systematically off, a little bit low on the low side, which are about 2.9 millivolts. If I go to 1 millivolt RMS, yeah, it seems to be very accurate on this one. It's maybe a little bit less than 1 millivolt, and on the 1 millivolt scale it's again it's reading a bit low, but it's consistently low. I guess it's just a tuning or something like that of the calibration, but that's as low as this will go. With the attenuator, of course, it's going to not be helpful. It cannot measure anything lower than this on a full scale like the other meter could at 0.1 millivolts. But then I think, given the bandwidth of this one, which is a bit higher, I think, and the fact that it can measure noise and other types of waveforms, I think this is a very useful instrument in its own right. So here's my last experiment or feature I wanted to demo from this instrument. The 400GL is the amplification, and I've connected right now the output of the 400GL from the back panel to the multimeter, which has should be easily able to handle a 1 kilohertz kind of signal, AC signal. So if I set the gain at the 10 millivolt level, I'm going to get 0.1 volt, because it's going to basically indicate 0.1 on this meter, which will be 0.1 full scale as far as this meter is concerned. So it's reflecting what this meter is showing. Of course, it's gained up the signal, so if you have an actual signal going into the input, you'll be able to see the gained up version of that AC signal. It's not a DC signal like in the previous meters where it's full scale reading of 1 volt or 10 volts or whatever. It's supposed to be full scale, but here you're seeing the actual AC signal at that frequency coming out on the meter. Now if I go to the 1 millivolt full scale, you should see a 1 volt signal coming out over there, and it's correct, and the frequency is also correct. As you can see above on the meter on the top, it says 1 kilohertz and reading a 1.0257 volts. So that's showing you exactly what the amplification factor is and what it can do with respect to the amplification. So if I go to a higher frequency, I can try 10 kilohertz and see if the meter will actually respond, the multimeter that is. Yeah, 10 kilohertz, so it's reading about the same. So the meter, this meter is able to do it. Of course, this can deliver up to 4 megahertz. Let's try 100 kilohertz and see what happens. So right now, this particular meter is not able to handle it. As you can see, it's down to 16 millivolts, even though this guy is putting out 1 volt on the back of the meter, but this cannot handle 100 kilohertz. If I go to 50 kilohertz, yeah, still not able to handle it. Back to 20 kilohertz audio frequency. Now it's got a full scale here, so it's pretty much dropping off rapidly after around 20 kilohertz, maybe 30 kilohertz. Let's see what happens at 30 kilohertz. Yeah, so it's down to 75 millivolts. It's a fairly rapid fall off in the gain for the multimeter. So if I connect the scope, of course I should be able to see that full signal. So let's do that next. Okay, so this is the meter connected to an oscilloscope. This time I have a 1 kilohertz signal, 1 millivolt, same thing, set on the 1 millivolt scale, but 1 volt output here, and I got a 1 volt RMS value coming out on this meter, on the scope as well. The only thing I don't get right now is that this has got a huge DC on top of it. So if I go to DC coupled, it's off the scale somewhere. It's sitting at something like 20 volts. I suspect there's supposed to be an AC decoupling capacitor in series with this output. Maybe it's shorted out, I don't know. It seems to be running at 20 volts, which is not good. So the meter didn't care before, but if I had connected this to some other electronics, it could have blown it. So I'm lucky I checked that. So there's something going on with this back output. It's got a DC level writing on it. It seems to be related to the power supply, which is around 26 volts. So I have to go back and look at that circuit and see what's that decoupling capacitor doing here. But if I otherwise the signal looks pretty good, as you can see here. There is a bit of a noise I was seeing earlier. Probably yeah, there was a significant noise. I think that's gone now. Probably a bad connection. So I have to turn the filter on, and it actually cleans up the signal a little bit. And if I go to higher frequency, it becomes more obvious, I think. So this is a very small 1 millivolt signal and bound to be noisy. Let's go to 100 millivolt signal here. Input. So this is 100 millivolts. I'm not seeing anything coming out at this point, which is strange. Okay, still on the 1 millivolt scale. Oh, that is frequency. I'm sorry, this is 100 hertz at this point, I think. Oh, I didn't. Oh, maybe not. I'm got confused a little bit here. Amplitude is still 1 millivolt. Okay. So go to 100 millivolts. Okay, there you go. Now it's 100 millivolts. 100 millivolt scale. I get a full scale reading there. Very clean, as you can see. The filter makes no difference at this frequency, which is fairly low. Now go to higher frequency of 200 kilohertz here, and definitely this amplitude has dropped a bit because the filter is on. I take the filter out and it returns. Again, a very clean amplitude, gained up by a factor of whatever, in this case 100 millivolts to gain of 10 in this case. So the effect of the filter is very clear now. So I just repeated the meter measurement, the multimeter, to see the DC level, and you can see that it's 22 volts DC with a 1 volt AC output for the same 100 millivolts at 1 kilohertz. So there's something definitely leaking, DC leaking to the outside world, and that's not good. I'll open up this meter again and then see what's going on with that output stage. Hopefully it's nothing significant and easy to fix, I'm sure. So once I do that, I'm going to also replace the plug with the IEC plug, and then I should be able to use any old cord to power this thing. The next few slides I'm going to be showing the removal of the old PH163 plug and putting in the new IEC 120 volt plug. So this is going to be just still photographs which I'm going to explain and talk over a bit. So here's the new IEC plug, and here's the old plug as it's installed currently with the two inductors, series inductors for cleanup of noise. And this is after I removed it. I used milling attachment on the Dremel to remove the screws, the rivets. And here's that socket which I took out, and it's in good shape even after removal. And this is the hole I need to expand to fit the new socket. Those pencil marks show the extent I need to grind down. So about 15 minutes later, I managed to file that down to required height. So 3/4 inch height for that new socket. And that's a new socket in there. Fits in very nicely. To drill holes, of course, to the hole didn't align as the previous holes, so not a big problem. And that's another view of that, showing that there's no interference with the bottom cover. There's quite a bit of shavings which fell into the bottom, into the rest of the instrument, so I had to vacuum that out and blow some air into it. This shows the right side with the right cover open, and this is the left side with the cover removed. So next I will test this new socket, make sure the instrument is up and running, and we'll do a few more things after that. Well, the moment of truth is here. I've connected the new plug in here, the IEC plug. It fits in nicely and no interference with the chassis or any of that. I've hooked it up to my 110 volt isolated supply in case I created some dumb short somewhere. I don't want to blow up something here. So I'm going to turn it on. I'm going to keep it on the minimum maximum resistance output on this with the lights here, and then I'm going to raise the supply voltage. I'm going to turn on the machine at the back here, so it's on. Raise the supply, and you can see it's coming on here without any problems. So let's turn on some more switches. So it's fully powered up, I think 110, 120, that's about 120 volts over there, and it's drawing about barely 5 watts of power right now. So it's fully illuminated, the light, and so we are online. So I'm going to move this back to the other bench and I'm going to apply some signals and see if that's still working correctly. Okay, so I have powered it up again on this portable bench of mine, and I've applied a 1 millivolt signal at 5 kilohertz, and you can see on the 10 millivolt scale it's just at about 1 millivolt. So it's going to be, of course, not very conclusive at this point, but if you remove the connection, it'll drop to below minus 20 dB. So now I'm going to apply a 10 millivolt signal, should go full scale. And so that's a 10 millivolt signal. As you can see, it is now full scale. And a 5 millivolt signal should bring it down to 5 millivolt on the nonlinear voltage scale. And there you go, it's 5 millivolts minus 6 dB. So the machine is back up and running as normal. One thing I forgot to do in all my haste of putting this back together was to check that output on the back side, which has the DC coming out at 22 volts. I need to check that again once I open it up the next time. Hopefully you might be able to also do the same repair to resurrect some old equipment with this plug issue or anything else. The one thing I forgot to, of course, mention was how did I fix this problem which I had with this initial problem that it wasn't working. I checked all the voltages, they were all within 5% or so, or even better in some cases. But the main problem was really the switch over here was noisy inside, and this switch is controlling the post attenuator, and that attenuator has got fairly low impedances on that particular selector knob. So anything that is even remotely resistive in the order of few K, 10 kilo ohms, a few kilo ohms, would totally destroy the ability of this instrument to measure any meaningful signals. So I think the main thing was I sprayed it down with deoxit and cleaned the contacts a little bit, exercised the control a few times, and then it was pretty much back working perfectly. I mean, there was absolutely, the noise was gone, and the accuracy is right where it should be. I mean, I don't think I'm going to touch this at this point. There's no point in calibrating it. The inside looks very clean, nothing burnt, no repairs done. So this is a pristine unit as far as I'm concerned. I thought I would look at this output DC level that is showing up on the output rear terminal. This is the positive one over here and the negative black terminal here. As you can see, one is grounded to a chassis and the other one is coming off this capacitor, which is a 50 microfarad capacitor. And the voltage on this side is around, actually this is a little bit higher, I was measured earlier, it's about 22.5 volts on the collectors of this NPN transistor. And this is a 24K pull down resistor to ground. So I'm measuring 22 volts here and about 22.5 volts on the other side of the capacitor. So I'm going to show you that, which means there is a half a volt drop across this, and if this 22 volts here, there's about a milliamp of current flowing to ground, which would imply that if you take the half a volt drop, a 1 milliamp current through this capacitor would imply a impedance or a resistance of this thing of about 500 ohms or so. So I thought I would try a different way of debugging this instead of cutting it out and measuring this thing, because this capacitor over here, which I suspect is a problem, is difficult to reach in terms of getting it out, because the bottom side of the PC board is very close to the chassis, which is also metal. So I had to remove a bunch of screws, pull the whole thing out, disconnect some connectors and whatever. So I thought I would do a simple experiment before I have to actually do it. So what I'm doing here is this is the output circuitry with all the existing components shown here in this pinkish color. We have a 26 volt supply through a resistor to this transistor, which then is basically the output of that is being coupled to a capacitor into the output, which is the AC output, of course. So there's also a 24K pull down resistor on the output of this thing. So normally it should be able to maintain a 0 volts here if this is not leaky, but if it's got some fairly low resistance, it's going to of course transfer that voltage off to here, and this will still continue to draw that small current, still keeping this voltage, DC voltage, sufficiently high, which is what I'm seeing. So what I'm going to do is, what I've done is, first of all, I measured with this is a test resistor I put across the output, which is a decade box. Initially it's going to be infinity, so there's nothing connected. So what I measure, of course, is what the meter is showing right now, which is RT is infinity, VC is 22.5 volts, and this VO is 22.4 volts. That means if I calculate the current that is flowing through this resistor, there's no output current here, so all the current must flow through this 24K. So then I would get VC minus V0 upon V0 over 24K is approximately 0.1, which is this minus this, divided by 1 milliamp, which is V0 over 24K, V0 being around 22.4 volts. So it's very close to 1 kilo ohm, this leakage resistance. It's not going to be constant. Depending on the leakage, it might change, since this is not a very linear component here at this point, the leakage itself. If now C26 is leaky, we can then say, if you put a lower value resistance here, then we can start affecting the voltage at this point, and basically completely be responsible of this by this capacitor leakage. So if I put a 1K resistor here parallel with the 24K, it effectively still remains around 1K because this is fairly high. So, and then the current that flows through this capacitor would be 22.5 divided by the total resistance through here, which is going to be the 1K here of the capacitor itself plus the 1K which is pulling it down to ground. So that current will be around 11 milliamps. Then we can calculate the voltage at this point would be 22.5. Of course, it might drop a little depending on the output impedance of this whole thing here, of the supply and the ability to drive current. So 22.5 minus 11 would be approximately, this 11 milliamps times the 1K would be 11 volts. So that's 22.5 minus 11 volts is around 11 volts. So let's see if we get something close to that, which then, if that's true, then we can basically confirm that this capacitor is most likely leaky. Okay, so what I have now here is the negative side of the capacitor, which I am looking at, which is connected to the meter over here, and it's also connected to this green wire to this decade box over here, and it's currently open, so there's nothing connected here, only one side is connected to ground. So I'm going to now turn on the supply and look at the voltage which is at the output of that capacitor, negative side. It should be around 22, yeah, it's about 22.5 volts. So the other side is a little bit higher, just slightly by 0.1 volt or so. So this capacitor is resistive, but it's not totally shorted out. So what I can do now is I have a 5K at this point over here on this decade box. So putting that to 5K, you can see the voltage is dropped about 3 volts or so, 2.5 volts. But if I go down to this 1K which I was talking about, this is 2K, now 1K, it's now down to about 13.5 volts. If I don't want to go too much more than that, because then I'm not sure if that supply can actually drive too much current. I might do damage to it. So I'm going to leave it around this value and see. You can say that it's got significant leakage. I mean, it's that 1K resistor is actually contributing to a large voltage drop, even with the 1K pulling it down here. So I think I'll have to at least lift the capacitor and measure it and see what's going on with it. Let's do that. I'm going to measure the capacitor next. So I connected the capacitor across, I've lifted one side, the negative side. I connected this capacitance meter at measuring the ESR at 100 Hertz, which I think is reasonable for a low frequency capacitance. I'm seeing a wrong capacitance value about 82 microfarad and a ESR of 15.4 ohms, which I don't think is good. So I'm going to replace this cap and see if that makes any difference to the performance of this thing. Okay, so I put in a 47 microfarad 63 volt capacitor, as you can see there, the one that is standing upright, and it seems to be much better now. I think the leakage is still there, but it's quite small. It's about 2 volts and it's dropping. So the ESR of this particular resistor capacitor was around 1 ohm or so it's a lot better, and I think that helps. I don't think this particular meter is going to give you absolutely a 0 volt output because of the size of the electrolytic. It's going to be leaky. Maybe they should have designed it differently. If you have a circuit that's sensitive to DC voltages, perhaps you should reconsider changing that capacitor to a different type with a lower leakage. At the cost of possibly lower frequency, the low frequency response may not be as good. I think they are using it to be able to transfer low frequency AC signals out, so you need a large capacitance value. You may need to use tantalum or something that is got better leakage. So I think that's probably going to stay with this particular capacitor right now. I definitely didn't like the 22 volts there. It's now well under control. It continues to drop. I guess the capacitor is forming, or it's getting less leaky, and I probably can test it on my capacitance leakage tester. I'm going to do that with the other cap and see what it actually shows at 25 volts leakage. And here's the final test with an actual 1 millivolt signal coming from the function generator. You can see it's 1 millivolt, 0 dB, and this meter is reading a 1 volt AC signal on the top, and then the DC level is 0.085 and is dropping. So I think I finally solved the problem. So here we come to the end of this rather long video, almost 53 minutes. I hope it was informative, useful. I tried to cover as much as I could. Maybe I was a little bit repetitive in some places, but I did cover a lot of material, and I was doing various things and debugging as well as testing it. So anyway, this turned out to be useful and interesting to me as well. So until next time, see you. Bye.